No, it's my pleasure to introduce Justin Wood, systems engineer at SAIC with the, I only know the acronym. They've spelled it out for me here. Fleet Numerical Meteorological, there's no T in this, Meteorological and Oceanographic Center. Thank you.
It's actually the Fleet Numerical Meteorology and Oceanography Center. That's the last time I'm going to say that, so you can just say Fleet or FNMOC. I work on a team of about a dozen people supporting our HPC environment. We all do, we have different roles and different jobs in that group. We're down in Monterey, about an hour and a half south of here. So I thought what I'd do is, we're not really out there known by a lot of people, so I'm going to give kind of an overview of what we do, what our products are, and how we use PBS to basically produce these products. So in short, we're really the only operational weather center in the world modeling the weather at all three levels of classification, so unclass, class, and top secret. The second bullet point, we're the only facility modeling the global atmosphere to DoD information assurance standards. If you know anything about DoD IA, you should feel sorry for us. In all seriousness, this is a very difficult task, at least for us, to accomplish. We provide support to naval operations mainly, and I'm going to go into some more detail about what we do. So we do maritime forecasting, basically ships at sea. We have two weather centers. We have one in Norfolk and one in San Diego, fleet weather centers. So we provide data to them so that they can provide forecasts. We also provide forecasts to ships, individuals, teams. We also do aviation forecasting for Navy aviation assets, which I'll go into more detail on that in a minute. We support basically deployments of Navy operations worldwide. We do anti-piracy support. We do some drug interdiction in the Caribbean. I believe we support the Coast Guard in that effort as well. I mentioned the fleet weather centers, and we also support the JTWC, the Typhoon Warning Center. This is kind of there's a lot of information here, but basically the Navy runs a series of models at increasing resolution. So we run global models. The output of the global models feeds the regional models. That's at a higher resolution and a tighter area. And then that output also feeds as the input to our local models. Just some examples here in the middle section. You can see, I think it's called the Navy Coastal Ocean Model, or NCOM. You see the east coast of the United States there. On the middle bottom section, this is airwaves over the Sierra Mountains. And in the local area, bottom right there, that's Groton, Connecticut. So we provide a lot of very detailed local models of different ports worldwide where we have assets. That helps to determine, actually, basically it helps in the decision making of the fleet. An example I was given is, let's say that there's a typhoon or a storm coming up the eastern seaboard, and the fleet is at Norfolk, it's in port. There's a major decision, which is, do we leave the fleet in port and we weather the storm, or do we sortie the fleet and go out and try and miss it? It can cause, basically to sortie the fleet is several $1 million to ramp up, fuel, and it takes time. But if we left the fleet in port and there was a major storm, we could incur even more damages to ships and subs. So that's a big deal for the Navy, and they depend on us to provide the data and to allow them to make those types of decisions. I'll continue. So this is kind of showing our piracy forecast. So I mean, humor aside, this is something that we've developed and we're still working on. And basically it's, we're fusing our atmospheric models with satellite images and intel information to give the fleet basically an idea of where the highest probability of piracy is going to occur, rather than police, the entire coast of Somalia out to, several hundred miles. We can give them at least an area where they can focus their efforts. I don't think it's perfect by any means, but this is just one of the examples of what we provide to the fleet. As proof that the DoD doesn't just spend money, we developed a product at Fleet, at FNMOC, called OPARS, Optimum Path Aircraft Routing System. And this takes the data and the numbers that we crunch, and what we do is we provide optimum path routing to 97 aircraft. And calendar year 2010, we were able to save $14.2 million in fuel costs. We already had the data. All we had to do was provide a method for the aviators to go in, and I think that, I don't know how they do it exactly, but the type of aircraft, where they're going, when they need to go, and we provide an optimum path that will get them there when they need to be there, as well as save money on fuel. Just a little bit of quick detail about what sort of what we provide. So I didn't mention this earlier, but we're co-located with NRL. It's a Navy research lab down there in Monterey. We've got 150-ish personnel. I think about 60 or so active duty officers and enlisted, and then the rest civilians. NRL provides us with the codes. They're the meteorologists. We provide them with the equipment to run the models. Some of the we provide a lot of information for safety of the fleet, but also for the warfighter to make tactical decisions based on these forecasts. Whether or not to put a team of SEALs on a beach at a given time, when a sub should surface. I mentioned earlier, we do submarine forecasting. There was an incident a while back when a sub surfaced and some sailors exited the submarine, and they weren't aware of the weather. They were washed overboard and never recovered. So since that time, basically, FNMOC has been given the mission of providing forecasts to submarines worldwide. The information that we provide also is relevant to things like weapons choices, whether or not to use laser-guided weapons. If there's a sandstorm, that's not going to work, so it gives teams the ability to decide not only when and where to deploy, but what gear to take with them. Now, I was a French major, not a Greek major, nor a math major, so I cannot explain this slide, but this is I just put this in here to demonstrate what NRL does. I mean, they're the PhDs, they're the meteorologists. They write the codes and do the physics, and that's kind of, for us, that's under the covers, but this is just an example of some of the black magic that happens. This wagon wheel, I'm not going to read everything off of here, but just to give you an idea of, in the middle, there's a numerical weather prediction, and there's some of the types of models we do, as I said, global, regional, aerosol, and then around the outside of that wheel, you'll see some of the products. I mentioned target weapon systems. OPARS is up there. I didn't mention search and rescue, or SAR, earlier, but we're called upon to provide data for a lot of search and rescue missions. If a plane ditches in the ocean, we'll be asked to provide current information, wave information, to help determine where debris and wreckage might end up. And we also I thought this was interesting, we do hindcasting to figure out where we can go to look for these items or bodies in unfortunate incidents. Just a brief overview of some of the models that we run. These are kind of we run several models. These are the big hitters. NOGAPS is our global model. COAMPS is a regional model. WaveWatch 3, we actually have the guy who's in charge of that is a surfer, so he has a vested interest in making sure that that is an accurate model. This just will show you sort of the interaction between these models. NOGAPS is run first, and it feeds almost everything. You see it'll feed COAMPS. COAMPS feeds WaveWatch 3 as well as NOGAPS. So all these models, they're not really separate, they're very intertwined. It's important that they run in order, and because, like I said earlier, the output from NOGAPS is the input for COAMPS, as well as other items. COAMPS, so we run about 40, I think, of these COAMPS regional models across the globe right now, at least in our unclass operations. And you can see some of the, up on the map there, you'll see the boxes of the different regions. That may be out of date, but that kind of gives you an idea of what we're able to do is we can pick a area of the world and run these forecasts. And they run at a higher resolution, obviously, than the global model. Our ensembles, this is based on NOGAPS, and the way it was explained to me is we will run 20 different members, and at the beginning, the physics of the input is tweaked slightly in each one of those members. So they'll run 20, and you'll see sort of this graph here on the bottom left shows the 20 runs, and on the right, obviously, that's kind of the output. And you'll see that where these lines converge is where we get a higher probability of an event, of gale force winds, for example, in this one. So that'll be where the red section is. That's the greatest probability. And where these lines diverge is where you'll see the lower probability. It just gives us the ability to get a greater probability of an event that we're looking for. One of the nice things about COAMPS is that we're able to spin those areas up very quickly. This is an example that we did for the Deepwater horizon in the Gulf of Mexico. We've also done, I believe, when the Fukushima incident happened, we were within a day, we were ramped up and we were running models, providing that input to the Navy and individuals that's above my pay grade, but the people from the fleet ships are able to call in and request areas. They can actually get on through the network and can request areas, and we can be running these areas operational within a day. You want me to go back? Sorry.
No, that's good.
We also provide a number of satellite applications. So we'll basically mesh our data with satellite imagery. And NRL has been able to develop a method. Again, I'm speaking out of my area of expertise here, but they've been able to figure out a way to pull dust plumes and stuff out of these satellite images that otherwise wouldn't be possible. So we provide, forecast. You can see basically the output from our models is meshed onto these satellite images. The short story about this slide is where we're going is we're always seeking to increase the resolution of our models, increase the accuracy. Now, what does that mean for us in the HPC group? With COAMPS, in the near future, they're looking to double the number of vertical slices and increase the horizontal resolution by, I think, 1.5 times. NOGAPS, there's some big changes coming down the pike as well. So What that does for us, we don't know exactly how that's going to affect the runs, although we have a pretty good idea that it's going to increase the runtime and it's going to increase the need for more nodes to be able to handle this load. So I'm going to talk a little bit about our installation of PBS at FNMOC. I don't know how everybody else runs, so I'm not trying to say that we're better than anybody else here, but for us, operational means more than just the cluster's up and running and users are running jobs. We probably have between 6 and 9 clusters at different classification levels. Basically because we have to run those different classifications, we have alpha, beta, ops at these different levels. So on, say, our alpha systems, we have a bunch of users, it's kind of the Wild West, that's okay. But on our operational box, it is critical that we run certain jobs at a certain time for a couple of reasons. One, I didn't mention this earlier, but we ingest on the order of 18 million observations a day from satellites, gliders, buoys, aircraft, ships. In order to run our models, we need that data first, and then we can't skip, say, the global model because we require the output to feed the regional model. So we really have a tight time frame, and then we have customers, and our customers are guys on the pointy end of the spear who require the data when they need it. So, skipping ahead there, we have a really strong requirement to minimize downtime. Any downtime greater than 2 hours requires someone with a star on his shoulder to approve. Any unplanned outage greater than that goes straight up the chain. We don't really use a complicated scheduling configuration yet. We're not doing hooks. We're not doing a lot of what I saw yesterday, but we may get there. Another thing is if we have a large downtime, it becomes very difficult to start up again after that outage, depending on how long we've been down. It's really hard to recreate the atmosphere if you've missed a big chunk of time. Last year we transitioned to PBS Pro 11. We went to 11.0 first. We had major heartache with that transition, and I'm going to start with the cons, I'm sorry, but we continue to have some database problems. It's not all the time, but I will say that 2 days ago on Monday, our operational box was down for a greater portion of the day, and that gets really frustrating when there's people in uniform standing over your shoulder watching you type. Pros, however, and this is a big deal for us, and I'll show you why in the next slide, but our queue times went down significantly on a couple of systems where we were able to measure that. Our alpha system, we're not necessarily as concerned about that, but that's a good thing. On our ops box, if you multiply 3 seconds by on the order of 50,000 jobs a day, which is what we run on operations, that's several hours of time saved. And that is a big deal for us and will be going forward as we have to increase the resolution of these models. This, you need to sit there while I read all the names of all these jobs. Basically, this is unclass operations. This is one watch. We run 2 watches per day. So you can't see the scale probably, but this is 0Z to 12Z. If you were to look at 12Z to 0Z, again, it's pretty much a replication of this with a few minor tweaks. But if you think of it like a player piano, as I said, on alpha, users run whatever jobs they want. On ops, it's a lot more strict. So all these little names that are obscured, you can't see, these are parallel only jobs. This blue line on the bottom, that's node usage. We run several thousand more serial jobs than we do parallel jobs, and that's where that queue time comes into play for us. But as you can see here, we're not really shooting for or concerned with, maintaining 80% usage or 90% usage of our nodes, we really need to make sure that the peaks don't go over that red line, because that slows things down, and then we can't get our products out on time, and then the admiral's notified, and it rolls downhill back to us. So, and unfortunately, we can't take these low times and backfill some of the jobs back in there, because we either haven't received the observations yet, or we haven't got the output from our global model. So what we're seeking to do here is, and unfortunately a lot of the jobs run at +4, which is this big spike, vertical spike right here. So as we increase resolution and increase slices, that spike is going to go up. What we're seeking to do is try and squish that down and stretch out that plateau a little bit. But we're getting there. But I guess I just wanted to point out that I think that this is why we are maybe a little bit different from other sites where we're not, at least on operational machines, we're not trying to make sure we maximize node usage all the time. We're more concerned about getting products out the door when they need to go out the door. Are there any questions?
So you mentioned you did unclassified, classified, and secret. So this is all
top secret.
Top secret. This is weather forecasting. So I was wondering what the difference between the three.
So it's not the weather that's classified. I had the same question when I started there. Why is that weather any different from this weather? It's not the weather that's classified. It's the area where we run those models. So, I don't even know, and I wouldn't tell you if I did, but if a SEAL team wants to do some mission somewhere in the middle of some unnamed country, depending on basically that mission is going to be at least classified, if not top secret. So, for example, our global, I think currently what we do is we run the global model unclass, and we push that data up to the classified side, and then from there we can run these regional models at that level. So it's basically to prevent people from knowing where we're running these models, because that could impact the mission. Does that answer your question?
So do you primarily use dependencies to sequence the jobs with each other, or?
I think to some extent we do. We actually use a product that I'm not totally familiar with. I think it came out of the UK called SMS, and that helps us to, I think that, this, like I said, think player piano, this kind of script is in there. But there are dependencies on, when one job runs, wait and make sure that Cameron might be able to better answer this question.
So that's true. We also have a lot of the jobs, when they finish, or as part of their completion, they submit and queue up other jobs. So you have these enormous long chains of jobs, and one breaks and it kind of messes things up. But we have long chain jobs.
Other questions?
Are you getting me back from yesterday, Vincent?
Not at all. No. 5 questions. So, no, I missed a little bit of the early part of your talk, but I don't know if you covered, is your workload entirely batch, or do you have any interactive types of jobs coming in the system?
At the operational level, the only people that I know of who run interactive jobs are here on stage and at that table right there. There may be some at the alpha and beta levels where there's more users running jobs as opposed to ops, but.
So we have a watchboard that they have to maintain and manage the systems So our watch floor, they will actually, they have the SMS display and then we'll show what's going on. If they have to run a sub-WEAX or one of the others, they will actually kick it off at specific times. So they at 12Z, they have to do this. At 14Z, they do, or at certain times, they will kick off a sequence of jobs.
Okay, time for one more question. Okay, giving it back to Vincent.
Actually, the reason why I was asking that is getting to these output maps, these contour maps that you have. So are they streamed during the run, as in something that the scientist could use monitoring at runtime, or are they just produced once the computation is completed?
I believe it's the latter.
Okay, okay.
I mean, there's also, post-processing done after the job has run. So I don't think there's any type of, while it's running, here's where the clouds are going to go.
It's convergent type. I mean, the calculation is convergence. So, it iterates and until it comes down, converges to a quantitative result.
All right. Thank you very much.
Thanks.